Okay. Do you still remember what a simple group is? Is it okay? What are simple groups? A group is simple if it has no
proper subgroup.
Non-trivial. No
Yes.
non-trivial normal subgroup. Okay. Let G be a group. And G is simple if G has no non-trivial normal subgroup. If you don't remember what this means, okay, now we have a group G, right? Oh, proper. This is important. Proper, non-trivial, normal subgroup. Okay, so this is the group G. If you have a subgroup and you have just a subgroup containing the identity, right? This is called the trivial subgroup. This is called improper. If this is not equal, this is proper, non-trivial. Okay, because you can have proper, trivial. If G is not E, meaning E plus plus, okay, this will be proper but trivial, right? G is also a subgroup of G, because G is called the improper subgroup of itself. We want the proper, okay? So that's why I said proper, non-trivial cannot be just E. Normal. What does it mean by normal? So we have H is normal in G. If AH is HA for all A in G. The left coset is equal to the right coset. All left cosets are equal to the right coset. So H is normal in G. So this is a simple group, right? So you're given a group, you see whether it has a normal subgroup or not, and whether the normal subgroup is proper, non-trivial. Once you find one, it's not simple. Okay? If the only normal subgroup is this or this, then it is simple. Okay? In other words, G is simple if its normal subgroups are just the trivial subgroup and itself, or the improper, right? So the key is to check whether a group is simple or not. Try to find the normal subgroup. Okay, if there is a normal subgroup which is proper, non-trivial, not simple. Okay, if you cannot find all the subgroups are not normal, so the only normal will be just the trivial in itself, then it's simple. So the key is you have to find the normal subgroup. Okay. Okay, next one, we see some examples or theorems. Okay. I call it a theorem, or if you don't think that it's too big property, you can call it proposition. Okay, I call it theorem. All abelian groups are not simple. So you have to get used to proving in general. Okay, you cannot give a proof in general given an example or specific. Okay, it won't cover all. Okay, now how do you prove this? Let G be an abelian. Then abelian group means what? GH is HG for all HG in G. Right?
So normal.
What was it?
It is become normal if J abelian.
Yeah. Thus, GH, right, is HG for all subgroup. This is the definition of normal, right? So, if H is a subgroup of G, then H is normal. Okay, so this is the proof actually that all subgroups of an abelian group are normal. This is actually in undergraduate in bounded algebra, right? So if G is abelian, every element commutes. GH is HG for all HG in G. So if you have any subgroup H, GH is also HG because the definition of GH is like this, right? Okay, so you can just do this. So if H is a subgroup, then H is normal. So what does it mean? It means all abelian groups are not simple. Because all of their subgroups are normal. That's the key. If you have a subgroup that is normal, not simple. Okay? So that's what I put there. If all subgroups of an abelian group are actually normal. So this is the proof. Why is it normal? Okay, so it's not simple. The second one is if you have a subgroup, a proper subgroup H of G with index 2, then G is not simple. If G is a group, H is a subgroup of G, such that this is true. Okay, if G is a group, H is a subgroup of G with index 2, then G is not simple. Okay, this is from previous course. Okay, if the index is 2, you only have two cosets, right? One is H, one is AH. You only have two cosets. The index is 2. The index means the order of G over the order of H, and by Lagrange theorem is actually the number of cosets. Okay, so you only have two cosets. H is H, the right coset, H is H. The other one, what's left is HA. So H has to be equal to H. AH has to be equal to HA. So H must be normal in G. So if H is normal in G, thus G is not simple. Once you have a normal subgroup, automatically not simple. Okay. Okay? Okay? Okay, next. Theorem 3. All cyclic groups of prime orders are simple. It didn't say all cyclic groups, but it says all cyclic groups of prime orders. Why? You have to find a normal subgroup, right? Okay. You remember we said if G is a group of prime order, then G is abelian, right? If G is a group of prime order, then G is abelian. That is one way. Since that G, so doesn't mean cyclic groups. It can be any group, right? Any group of prime order. But I just put cyclic here. Yeah, actually. So let G, I just put accordingly, be a cyclic group of prime order. Okay. I put this. Actually, you can put generator, right? If you want. Okay. Let G be a cyclic group of prime order. Then, if H is a subgroup of G, yeah, erase this first. By Lagrange theorem, okay, what does Lagrange theorem say? Can somebody?
Teacher, order of H most divided order of J.
Right.
So because order of J prime, so not any divided only J, only B or 1. So
Right.
not any subgroup of J order B, prime, for prime order.
Okay, so that's right. By Lagrange theorem, the order of H divides the order of G. Now, G is a group of prime order, so the order is P. So what are numbers that divides P, a prime number? Only 1 or P, right? That's the only number that divides a prime P. So it's only 1 or P. If the order is P, is the group G. If the order is 1, is the trivial subgroup. Okay,
Yes.
so the order of H is 1 for P, thus H is this or H is G. Okay, so this means that G is simple. Okay, so it's just by looking at the subgroup. Is it normal or not? If there is no proper normal, then it is not simple. If it is, if there is no, that is simple. Sorry. If there is proper normal, it's not simple. Okay, that's the key. Okay. Now we go to, okay. Oh, theorem 1.4 is exercise. Exercise means make sure you try this and I can ask in the next class. Okay, let me write. Theorem 4. An abelian group is simple if and only if it is finite and of prime order. Okay. Okay. So I will not write the proof here, but I will just give some hints, yeah? Proof. So you will put, let G be a group. Okay, then you show this one. If G is abelian, if G is abelian and simple, right? Then G is finite and has prime order. Okay, you assume G is abelian and simple, meaning there is no, I will give you the answer. There is no normal subgroup, right? So you have to show this. You can show by contradiction, right? You assume the order is not prime, and then show that it's a normal subgroup, meaning it's not simple, a contradiction, okay? And you can assume this way, let G be finite and of prime order, then if G is abelian, it is simple, okay? So you go the other way around. Okay, you try this. Okay. Now, next is theorem 5. Theorem 5 said 2 or less. Proof. There's another one that you need to find. Okay, I didn't give the proof there because I want you to find it and try to understand. Okay, if you can type, then it's easy for you to share in the next class. If you write, you have to scan. So if I ask, okay, Vian, can you share the proof? Then you can share. Okay, and we are in the same WhatsApp group. So if you need someone to check your answer or compare or discuss, you are very welcome. Okay, I'm sure you don't mind, right? To contact each other. Okay, just know each other and try to discuss. Okay. So what does it say? Suppose G is a group of order 2 times n, and n is odd, n is bigger than 1. Then G is simple. Okay, not simple. The easiest. Okay, besides Fauzia, because I have heard your voice. I want to hear someone else's voice. Okay, can someone give me an example of the smallest non-abelian group? Smallest non-abelian group.
S3 group.
S3. S3. Okay. S3 is the smallest non-abelian. You know permutation group of order 6? Yeah. Okay. So you have to remember, this is from undergraduate, the list of elements, right? 1, 1, 2, 1, 3, 2, 3, 1, 2, 3, 1, 3. 2 permutations, right? Permutations are 1 to 1 and 1, 2. So the order is 6, which is 2 times 3. So by these 2 odd tests, it is not simple. But if we don't use this theorem, you can actually find a normal subgroup, right? What is the normal subgroup? One with index 2, right? So we have done this before many times. This is a normal subgroup of order 3. So the index is 2. The other 3 subgroups of order 2, they are all not normal, right? Remember? This is also what we call a silo 3 of S3, right? That's why you need last semester's notes with you. You cannot keep it anywhere else. You have to remember all this. I assume you know all this. So by definition, this is a normal subgroup which is not trivial and proper. So by definition, you have a trivial, not trivial, what is it? Non-trivial proper subgroup. Okay, you have a non-trivial proper normal subgroup. That's the right one. So it is not normal by this. But by this, much easier, right? The order is 6, which is 2 times 3. 3 is odd, bigger than 1, so it is not simple. Okay, done. The one that I give in the example, that is a group of order 30, which is 2 times 15. Again, 2 times 15, right? By this one is 2 times 15. So by 2 odd tests, it's not simple. If you write this, 2 times 15 is 2 times 3 times 5. If you go back to last semesters when you learning about silo theorems, right? You have silo 2, silo 3, silo 5, and it turns out that there is actually a normal subgroup, right? In this one. So actually using definition also. Okay. The last thing that I want to do today is the last theorem for today. So many theorems. Now, first day already 6 theorems, right? Okay. okay, which we call index theorem. Okay, let G be a finite group. So the order is less than infinity. Okay, finite group. H is a proper subgroup of G. Sometimes people put this, it's not equal, it's proper, such that the order of G does not divide the index of H in G factorial. Okay. Then H, okay, H is the one. H contains a non-trivial normal subgroup of G. Okay, so in particular, G is not simple. If you can find the proof, that would be nice. Yeah, I'm not expecting you to write it out or show it, but try and find it. It's quite long, but it's good for you to try and find it and see if you can understand the proof. Okay, then I give this someone outside. Oh, okay. Okay, let G be a group of order 20. So this is the example, yeah? Okay, this then, blah, 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 G is not simple. This is actually the point. Okay, now, example is the order of G is 20. The order of H is 5. Okay, if you have 20, you know that is subgroup of order 5 because silo, right? Remember silo? This is 4 times 5 prime power. Okay, you have a silo of order 4, you have a silo of order 5. So definitely you have a subgroup of order 5. Okay, now let's see this. Let's see this. What is this? G H is 20 over 5 is 4. And G H factorial is 4 factorial, which is 16. So 20, which is the order of G, does not divide 16, which is this, right?
24.
24. Make sure you are awake. That's what the teacher said, right? You make a mistake, I make sure you are awake or you are sleeping. Okay, I have a very good student here. All right, so G is not simple. All right, so this is what we will see today. And some more examples I will give on Wednesday, all right, in our class. Actually, these notes I wrote with the Faiz, the one in the seminar, and Dr. Hazira. And group theory 1, I wrote with Dr. Hidayat in the seminar just now. So we bring up together the lecture notes.